Hello everybody, I welcome you all to NCAS Geology class. Today I will discuss about crystallography, which is a branch of mineralogy that deals with the crystals. So let me discuss this crystallography. There will be a series of lectures on crystallography. First I will discuss how a crystal develops, how atoms get linked to each other to form molecules. Molecules get linked to each other to form clusters of molecules or motifs, and their arrangement in systematic manner to produce the unit cells and finally the crystals. So let us start. Crystallography is the branch of mineralogy that deals with the study of crystals and the laws that govern their growth, external shape and internal structure. So in crystal we see that crystal is a polyhedral body. Crystal is a polyhedral body bounded by faces, and these are the planes that bound a crystal, and these faces they reflect internal atomic arrangement. So atoms get arranged in a regular fashion so that the crystal develops. So we can say a crystal is a polyhedral solid and that presents a regular shape, and the faces or the sides or the plane surfaces that bound the crystal, they are called as faces. These faces that bound the crystal reflect the internal atomic arrangement. The atoms of elements combine to form molecules, molecules combine to form the building blocks that are called as unit cells, which get repeated in 3 dimensions to produce the crystal structure. So these unit cells are the smallest units that get repeated in 3 dimensions to produce a collection of unit cells which conform to a definite shape and structure, and this solid that comes into picture due to the collection of unit cells is described as a crystal. So atoms they join to form molecules, molecules to form a smallest unit which is called unit cell, which repeats itself in 3 dimensions to produce a bigger structure, and that structure is crystal. So in this manner the molecules, atoms, molecules or motifs, they get linked to each other, they develop the smallest unit, that is unit cell, and unit cell repeats in 3 dimensions to produce the crystal structure, and crystal shows many faces that bound it, and these faces are the reflection of internal atomic arrangement. So crystal is a solid, it is bounded by faces, and these faces reflect the internal atomic arrangement. And when you study these crystals, when we study the solid substances that result from consolidation of liquids or gases, so we see that solids, liquids and gases, they are the matter that exists in the universe. And these matter, they are either solid, liquid or gas. And crystals represent the solid states of matter. The solids may exist as non-crystalline or amorphous matter, single crystalline solid, or it may exist as polycrystalline solid. So we'll discuss the solid state of matter. So in amorphous solids, there is no regular atomic arrangement. So there is short range order of atomic arrangement. They are isotropic with low melting point and high energy state. In crystalline solids, there are atoms, molecules which are very closely spaced and are having regular periodic arrangement and a long range order. They show higher density, sharp melting point, low energy state because it is stable state, and anisotropy in atomic arrangement. But in case of amorphous substances, the energy state is high because of irregular atomic arrangement. They are not in a stable state, but they try to achieve stable state because of their higher energy level. In case of single crystalline solid, the atoms are regularly arranged without any dislocation or break, whereas in case of polycrystalline solid, there may occur breaks in atomic arrangement, as a result of which more crystals are found to be produced sharing common planes, or they can form crystalline aggregates. So this diagram shows a single crystalline solid showing atomic arrangement, and there is no break in atomic arrangement. But here, in case of polycrystalline solid, there is break in atomic arrangement. Here there is break. So crystals, they grow in this direction and in this direction. So they produce polycrystalline solid with breakage, with dislocation in their atomic arrangement. So solids exist as single crystalline solid or polycrystalline solid. It may exist as amorphous substance or as crystalline substance. In amorphous substance, the atomic arrangement is very irregular. It is in high energy state, so that the atoms can be arranged and a stable configuration can be achieved with formation of crystals. Thus we see that crystals show a long range order in atomic arrangement, and this arrangement reflects repetition of basic units or unit cell in definite way, so that the crystal develops. The way in which the basic unit of crystal structure repeats is called the symmetry operation. So a particular symmetry operation, these unit cells, they repeat. The regularity in arrangement of faces, edges, solid angles and inversion center of the crystals is described as the symmetry of the crystal, which is controlled by the atomic structure of the crystal concerned. There are 13 standard symmetry operations by which atoms get arranged in crystals. These are axis of 1-fold, 2-fold, 3-fold, 4-fold, 6-fold rotation, 1 bar, 2 bar, 3 bar, 4 bar, 6 bar. These are the axis of rotoinversion, 2 by m, 4 by m, 6 by m, they are the axes with planes perpendicular to the axis, or the mirror planes that exist perpendicular to the axis of 2-fold, 4-fold, 6-fold in 2 by m, 4 by m and 6 by m. So these are the standard symmetry operations by which the unit cells or the atoms they repeat so that the crystal develops. The atomic structure of crystals are studied by X-ray diffraction (XRD) and atomic force microscopy, and these studies they have revealed that the atoms are found to be arranged in regular manner with repetition of the smallest unit, that is unit cell, so that the three-dimensional structure of the crystals develop. Let us know what is motif and what is node. The atomic structure shows long regular arrangement of molecules, atoms, which actually get bonded with each other to form the crystal. This bonding results in development of complete or partial coordination polyhedra. For example, we can say that silicon and oxygen, they combine with each other to produce SiO4 tetrahedra. It forms a SiO4 tetrahedra. It is tetrahedron. The shape is like that of a tetrahedron, and the four corners are occupied by oxygen, and in the center there is silicon. So this type of arrangement, this is a type of arrangement. So it is a type of polyhedra. So atoms and molecules they combine with each other to form coordination polyhedra, as a result of which the crystal gradually develops. The edges and corners of the polyhedra, say SiO4 tetra polyhedron, it shows the ions with unsatisfied electrostatic charges. For example, if it is SiO4 tetrahedron, it has -4 charge. Silicon 4, oxygen -8, so it will be -4 charge. So it is having unsatisfied electronic charge. Therefore, it must have to link with other cations so that it will be electrically neutral. That happens because we know the crystals are electrically neutral, atoms are electrically neutral. So the atoms they join together form molecules, molecules join together to form polyhedra. The polyhedra shows unsatisfied electrostatic charges, as a result of which other cations are being attracted to neutralize the structure, or one polyhedra links with other polyhedra to gradually develop the crystal. In this process, a small cluster of polyhedra is formed that contains all the coordination polyhedra characteristic of the mineral and its chemical composition. So, in the neutralizing process, several polyhedra come together along with other cations, so that a cluster of polyhedra develops, and that cluster conforms to the mineral character, mineral composition, and it develops a structure which is the crystal structure. So minimum number of polyhedra they must be there so that it will conform to the chemical composition of the substance. In any mineral, we can recognize a small cluster of coordination polyhedra that contains the mineral's fundamental composition and unit of pattern or motif. It will contain some molecules and their arrangement in a definite pattern, which you can say it is a unit cell. As the mineral continues to grow, additional clusters of the same pattern of coordination polyhedra, or we can say the cations surrounded by anions as per coordination number, or such coordination polyhedra develops due to addition of anions and cations, so that the crystal structure of the mineral develops through a definite three-dimensional geometric pattern, which we can say it is a long-range three-dimensional crystal structure. So, in this manner, the polyhedra they get linked to develop the long-range order of the crystal structure. Clusters of coordination polyhedra are added with one atom or ion at a time as the crystal nucleates and thus form microscopic crystal, which become a macroscopic crystal gradually as it grows with addition of polyhedra from the environment till the environment condition becomes unsuitable for the growth. So, in the environment, the atoms are available, molecules are available. These atoms and molecules, they take part in the formation of the crystal structure till these atoms or molecules are made available for the growth of the crystal. The smallest unit of such cluster of atoms or molecules or coordination polyhedra that are repeated by a set of symmetry operation or by symmetrical rule will generate a long range order or pattern of the atoms which are characteristics of the crystal. This smallest unit of atoms or cluster of atoms or molecules which are found to repeat in 3 dimensions in order to give rise to the crystal structure are described as motif, a group of atoms or molecules which are found to be repeated in 3 dimensions to produce the crystal structure. And this motif may be SiO2, Si2O7, Si4, Si2O6, for example, Si411, Si2O7, Si309. Why we consider these? Because these are the silicon oxygen polyhedra. As you see, most of the rocks and minerals of the earth crust are made up of silicates. So, silicon is an important component. That's why we take into account the Si4 tetrahedron as the building unit, which gets linked with other building unit of Si4 tetrahedron, and thus different types of links of the Si4 tetrahedra develop, conforming composition to SiO2, Si2O7, SiO4, Si2O6, Si4O11, Si2O7, Si3O9, like this. So, these atoms or molecules, they form a motif which is found to be repeated in 3 dimensions to produce the crystal structure. If any point is used to represent the motif in the crystal structure, it is described as a node. Any point where the repetition occurs, repetition of the motif occurs, that point is called as a node. So node refers to lattice points or positions in space where a motif is repeated. Thus, if it represents a location, thus node represents a location where the atoms occur together, and thus node is not the actual atoms, it represents the position where the atoms occur, and the position of atom nodes occur in a systematic pattern in which the atoms can be arranged like this. So nodes locate the position where the motifs or coordination polyhedra they occur in a systematic manner. Systematic arrangement is the arrangement of nodes or the lattice points. All nodes are identical and equally spaced, but motifs represent a single or a group of atoms or coordination polyhedra that provide the actual chemical information of the mineral. Thus, a crystal structure is the combination of nodes and motifs. Nodes give rise to the systematic arrangement where atoms are found to be arranged. So, nodes locate the position of position in the crystal structure where motifs or actual atoms occur. Step by step visual explanation of nodes or lattice point and motif which form the basis. So nodes are the lattice points. So these are the lattice points or the nodes. These dots are the nodes. The arrangement forms a space lattice. This is a space lattice. This is a space lattice. Space lattice is nothing but it is a geometrical arrangement. It refers to geometrical arrangement referring to the site where the atoms are to be repeated, and this lattice that does not represent the atoms. This lattice is the position where the atoms are found to be repeated, and in this position the atoms are being added or motif is being added or motif is being attached to these nodes. So here this is the nodes, and each node is being attached to a atom. One atom is attached to each node. Each node carries a motif made up of one atom. This is a type of crystal structure. Similarly, the motif represented by more than one atom, the two atoms they are located in the same nodes, same lattice points. So this gives rise to a pattern of atomic arrangement. So in this manner, the atoms are found to be repeated in crystal structure to develop the crystal. So motif is the actual atoms, in nodes provide the site where the atoms occur and are repeated in order to develop the crystal. So now let us see what is unit cell. A small repeating unit of motifs in space lattice is the unit cell. Let us say this is the unit cell, which contains 4 sites where 2 atoms are being repeated, and this is the smallest unit, and it can be repeated in this manner. It can be repeated in this manner to give rise to silicate structure. It may repeat in this manner, it may repeat in this manner, it may repeat in this manner in a systematic pattern, it may repeat in this manner. So in 3 dimensions this repetition takes place so that the crystal structure develops. The crystal structure can develop. In this manner, if they are arranged, we can see the formation of the pyramids. Pyramid-like structure can develop. So unit cells are repeated in 3 dimensions to give rise to the silicate structure. So nodes are added with motif. Motif are found to be repeated in space, and it finally results in the crystal structure. And there are several operations by which this regular arrangement of motifs takes place, and that is the symmetry operation by which this repetition occurs. In my next class, I will discuss about these symmetry operations. Thank you all for giving a patient hearing to my talk. Now, I will discuss about the symmetry operation which operates about these arrangement of atoms and molecules, as a result of which the crystal structure develops. The symmetry operation, it may be a simple symmetry operation involving one type of operation such as translation, rotation, reflection and inversion. Translation with respect to distance, rotation with respect to an axis, reflection over a plane, inversion about a center. So these are the simple symmetry operations by which atoms and molecules are found to be repeated in crystal structure. Or there may be compound symmetry operation involving more than one type of about 4 types of operation. There may be translation along with rotation, rotation along with reflection. So this will be a compound operation. Let us discuss what is translation. It involves periodic repetition of nodes or motifs by a systematic linear displacement. The translation is defined by unit translation vectors such as t, which is of specific length, and there is a direction along which the displacement takes place. For example, if this is a motif, this is repeated in one direction at an interval of t. This is the motif at an interval of t. T is the translation vector. So in this manner, the motif gets arranged. So this is called one-dimensional translation of the motifs, or we can say the atoms are arranged in this manner, with this much spacing, regular spacing in the atomic structure. This is one-dimensional arrangement with translation of t units. If the motifs are translated in two dimension. Two-dimensional translation is defined by two vectors Ta and Tb and by their direction. Here the pattern depends on the length of Ta and Tb and on their direction of translation. If Ta is equal to Tb and Ta is perpendicular to Tb, then what we will find? We find a square shaped arrangement of motifs and nodes, because Ta is equal to Tb and they are arranged in two dimension. This is a type of arrangement, this is a type of arrangement, this is a type of arrangement. So spacing is same, and angular displacement is 90 degree. So it gives rise to square pattern, square shaped. So the shape depends upon what is the length of Ta and Tb and what is the angle between them. Same thing, Ta is equal to Tb, but their angle is not equal to 90 degree. So here it becomes, this is not 90 degree. This is not equal to 90 degree. So we get a rhombic shape, because this length is equal to this length, but this angle is not 90 degree. So we get rhombus like arrangement of atoms, rhomb shaped atomic arrangement, as has been shown here. If the atoms are found to be arranged in three dimension, then a three-dimensional structure is found to develop. Let us see. This is a three-dimensional arrangement. There are three vectors Ta, Tb, Tc, which are the three vectors. Ta, Tb, Tc angle is 90 degree. In that case, what happens? We find that this is 90 degree, this is 90 degree. So in this manner, if the motifs are being repeated, motifs are repeated, so it will give rise to a structure like this. So it will give rise to cubic structure, three-dimensional pattern, because of this translation of the vectors or the translation of motifs in a regular fashion in three dimension, keeping the spacing constant and their translation at 90 degree to each other. It gives rise to cubic structure, or we can say it is a type of space lattice, which is cubic space lattice, and it shows an array of points where the points or nodes are repeated. What is space lattice? Space lattice is simply a arrangement of points in three dimension, as it has been here shown here like this, It is repeated in three dimensions, like this, like this. So this is repeated, this is repeated in this manner, this is repeated. So in 3 dimension the atoms and motifs are repeated to give rise to the crystal structure. So space lattice is the 3-dimensional pattern of arrangement of atoms, or you can say it is an array of points or nodes, motifs forming the space lattice, which are symmetrically arranged. Rotation. Now let us discuss what is rotation. Motifs can also be found to repeat with respect to an axis or line one or more times during a complete rotation of 360 degree. The number n denotes the number of times the repetition that occur in a complete rotation. According to the number of times the repetition occurs, the axis is described as an axis of 1-fold, 2-fold, 3-fold, 4-fold, 6-fold, corresponding to the repetitions at 360 degree, 180 degree, 120 degree, 90 degree and 60 degree rotations respectively. 360 rotation conforms to 1-fold rotation, 180 degree rotation for the motifs repeat, it corresponds to 2-fold axis of rotation, 120 degree 3-fold axis of rotation, 90 degree 4-fold axis of rotation, 60 degree 6-fold axis of rotation. There is no 5-fold axis of rotation, which can never be possible to give rise to a symmetrical arrangement. Let us say this is a motif. If it goes on like this, goes on like this, goes on like this, and here it comes to its original position. If this goes on like this and come to this place without having these positions, this position is repeated after 360 degree rotation. So this is 1-fold. Here this is repeated after 180 degree rotation. Then comes to its original position. It is 2-fold axis of rotation. Same motif here, it is repeating after 120 degree. After 120, here it is repeated. So this is giving to axis of 3-fold rotation. This is 2-fold axis of 2-fold rotation. This is axis of, here it is being repeated 4 times. So this gives rise to a square shape structure. The motif is repeated in every 90 degree rotation, or this arrangement is repeated in this manner, occurring here, here, here and here. So they are correlated with respect to a 4-fold axis of rotation. If the motifs are occurring like this, that means 1, 2, 3, 4, 5. So this is 6-fold rotation. 6-fold rotation. The same motif is repeated at 60 degree interval. 60 degree interval, like this. So it will complete 360 degree, and that axis will be the axis of 6-fold rotation. So in rotation, the crystal occupies same position several times, or a crystal face occupies same position several times. If it occupies same position in 360 rotation, then it is said to be having one-fold axis of rotation. If the same position of the faces or motifs repeated twice in 360 rotation, it is axis of two-fold. If it is rotated thrice in 360 rotation, then that axis is called axis of three-fold rotation, like this. In reflection, or in case of a mirror plane, the same motif is found to be repeated through a reflection over a plane. If this is the object is same object is appearing like this, then this is the mirror plane. If the motifs are occurring like this, then we can say they have a symmetry with respect to a mirror plane between them. So they are having the plane of reflection. So it is a in case of reflection, it is a symmetry operation in which every component of a pattern is repeated by reflection across a plane called mirror plane or M. Reflection occurs when each component is repeated by equidistant projection perpendicular to the mirror plane. Reflection retains all the components of original motif but changes its handedness. Sides are being changed. The new motifs produced by reflection across a mirror plane are mirror images of each other. Mirror image. The symmetry operation that changes the handedness of the motifs are called as enantiomorphic operations. So here this is the plane of the mirror plane. We have G on one side, exactly at same distance. G is repeated and it is having its mirror image. This G both are related to each other with respect to mirror image. They are the mirror image at same distance. So this is original motif, this is reflected motif, and we have a mirror plane in between them. So if the atoms are arranged in this fashion so that one is the mirror image of the other, in that case we say the crystal is possessing a plane of symmetry. Inversion with respect to a center, it is designated as I or C. It involves the repetition of motif by inversion through a point called the center of the inversion. Inversion occurs when every component of a pattern is repeated by equidistant projection through a common point or center of inversion. The two letters G in the figure below, they show enantiomorphic symmetry operation called inversion and show the center through which this inversion occurs. It shows this center is called the inversion center. So if it is a G, this position become to this place, this position come to this place, this position come to this place. So the entire object is found to be rotated with respect to this center, or the whole object is found to be reversed with respect to the center. So we define the center of symmetry how? For every point, for every edge, for every face in a solid, there is another face just on the opposite side at same distance away from a common center. If this is a face, This is the distance. At this distance, another face is occurring. This is the corner. This is the distance. At the same distance, another corner is appearing. This is the edge. This is the distance. Similarly, another edge is occurring at the same distance on the opposite side. So, we can say the inversion takes place with respect to a center. And the whole motif is found to be in reverse or in inverted condition with respect to that center on the opposite side at the same distance. If this character is there in atomic arrangement, then the crystal or that space lattice is said to possess a center of symmetry or the inversion center. Then we have the compound operation, which involves glide reflection, roto inversion and screw axis. So in my next class, I will discuss about this. I will discuss on this compound operation, symmetry operation involving reflection, roto inversion and screw axis. Thank you all for giving a patient hearing to my present talk.